In this video, we're going to start taking a look at the concept of equilibrium. So often in the past, when we've looked at reactions, we've considered that the reactions go to completion, meaning that you have one or more reactants and one of them is completely used up, which we call the limiting reactant, and product is created. So we say that the reaction stops once you've run out of one or more of the reactants, and that's called going to completion. And this can happen in an open system as you allow product to leave your container. So let's say I'm boiling a pot of water, okay, and if I have the lid open, as I boil the water, it turns from liquid to gas, and the gas will continue to be formed and escape until all the liquid has turned into gas. I've run out of my liquid and I've gone to completion. Now, if I had a closed system, you can actually start having the reaction start going in the reverse direction as well, not just going forward. So if I were to boil a pot of water and I put the lid on top of it, what you're going to start to notice is as the gas builds up, some gas is actually going to start turning back into liquid and condensation is going to occur and the reaction is going to go in the reverse direction. And what can happen is that eventually you will reach a state of equilibrium where the rate of evaporation is actually equal to the rate of condensation. And I'm not really going to have any more measurable changes in the amount of product or reactant. It's going to seem like the reaction stopped, even though it's just happening to occur at the same rate going forward and reverse. And this is actually what I do when I'm making like Sunday gravy at home. I don't want to lose all my delicious sauce, so I'll put the cover of my, the lid on my container so that this way it keeps cooking without losing anything to, outside the container. So let's define what equilibrium means. And a lot of times it's called dynamic equilibrium to make sure that you get the concept that there is still reactions happening. So it's when the forward and the reverse reactions occur at the same rate. So here, if we were considering the evaporation of water, which is a physical change, we would indicate that it's at equilibrium by putting these double arrows, showing it's not only going forward, it's also going in reverse, and it's doing so at the same rate. In order to reach equilibrium, there's a couple of requirements you have to have. The reaction has to be reversible, meaning it has to also be able to go in the reverse direction. So for instance, if I take an egg and drop it on the floor and it breaks, I can't go in the reverse direction. I can't unbreak that egg. So you have to have a reaction that's able to go both forward and reverse. The other thing you have to have is you have to have a closed container or a closed system. No reactants or products could be able to leave. So we have to make sure that we don't lose any reactant or product. It still stays in the container. And once I've reached this equilibrium situation, the rates of the forward and the reverse reaction are equal. So the amounts or the concentrations of reactants and products are constant. They are no longer changing. There's no observable changes occurring in the system. Yes, I still have movement going forward and reverse, but the total amounts of reactant and product are not changing. Okay, so how I like to think of equilibrium to kind of visualize this on a macroscopic level is I think of two rooms that are joined by a door. And let's say I have 9 people in this first room, we'll call that the reactant room, and I have 4 people in this second room, we'll call that the product room. Equilibrium would be if for every one person that leaves the reactant room to enter the product room, one person from the product room leaves to enter the reactant room. The rates of people leaving and entering are the same. So if I think about it from this level, okay, at one person leaves, one person enters. I still have the same number of people, 9 and 4. They don't have to be equal numbers. I have more people in reactant room than I do the product room. But these numbers are not changing. The amounts or the concentrations are not changing. And this will keep happening. One person leaves, one person enters, same rate. But there's no measurable changes. Now look, I do have movement, right? This guy was in this room. This guy was in this room, but now they're in different rooms. So I do have molecules that are changing from reactants to products and vice versa. But there is no actual changes in the concentrations. Okay, this has to be a closed system. So let's say I create a door over here, and now people start leaving this room through this door. Okay, now I'm losing people. This amount is no longer going to be constant. So it is no longer going to be at equilibrium if I don't have a closed system. Has to be a closed system in order to reach equilibrium. Then we're going to learn something later in this chapter called the Chatelier's principle. What is that? Well, it's talking about things you can do that will shift a system out of equilibrium and what's going to happen in order to return to equilibrium. So let's say, okay, all of a sudden I turn up the temperature in this room. What's going to happen? Well, these people are going to start leaving the reactant room and going into the product room at a faster rate than, the reverse reaction. So you're going to see people going to the right, pouring into this room, and it's going to shift out of equilibrium. It'll no longer be at equilibrium until we restore the temperature, and the reaction can then occur at the same rate. So you're going to see there's different things that can shift a reaction out of equilibrium as well. Okay, so let's talk about, how the AP loves graphs and charts and things like that. So let's just kind of talk about certain graphs or charts you might see. So let's assume that here's a reaction. I have A and B. My reactants turning into C and D products. These double arrows mean equilibrium. The forward and reverse are happening at the same rate. So let's say we start with, what we typically do is we typically start with all reactant when we start a reaction, right? We don't have to, but a lot of the times we do. So let's say we start with all A and B, only reactant. So when the reaction starts, I'm not going to be able to have any reverse reaction happening because I don't have any products. All I have are reactants, and they can collide. Through collision theory, we say you need to collide in order for reaction to happen and turn into products. So at first, I'm only going to have the forward reaction occurring if I only start with reactants. And so you have this on a different slide. At first, the reaction only proceeds forward. Over time, the concentrations of my reactants will decrease because they are colliding and reacting and turning into product. They're getting used up. So overall, the forward rate will typically decrease over time as I use up my reactants, and there would be less collisions happening between them. So if I was going to show you a graph of rate versus time, which we'll fill out slowly, we would start with our highest rate if we're looking at the forward reaction, because I have the highest concentration of reactant to start with if I start with all reactant. And over time, the slope of this is going to start leveling off as the rate decreases as reactant is used up. Okay, we're going to continue to fill out this slide, but let's just take a look. This you might not have. As time goes on, C and D are created. So as I get product being created, I am going to now be able to start the reverse reaction. And at first it'll be pretty slow because I don't have a lot of product made yet. But as I make more and more product over time, the reverse reaction rate can increase. So as C and D are created, they can react in reverse. The reverse rate will typically start lower, but it will increase as more C and D are made because I'll be able to have more collisions between them to result in a successful reaction. So if I'm plotting the reverse reaction, it would start at, if I have no product, it would start at 0, the rate, and over time, it would get a little bit faster. So notice that it's getting faster over time. Okay. Eventually, the system will reach equilibrium where I have equal rates. On this graph, they should converge to the same value. The forward and the reverse rate should converge to the same value. Okay, and that's how I know I've reached equilibrium. The rates of the forward and reverse reactions are equal. And remember, at that point, my concentrations of A and B, my reactant, and my concentrations of C and D, my product, should remain constant. They don't have to be equal. I don't have to have the same amount of reactant and product. I might have more reactant, I might have more product, but they have to be staying the same over time. So this is my graph of rate versus time. Okay, notice I start at different rates and they converge to the same value. The reverse reaction's getting faster until it gets to equilibrium. The forward reaction's getting slower. Now, if this were concentration versus time, the graph would look slightly different. Now, again, if I'm starting with all reactant, I'd have my highest amount of reactant to start with, and if I start with no product, I'd start at 0, and the amount of the concentration over time of the product would go up. Concentration of reactant over time would go down until eventually they are constant. Notice they don't have to be the same value. Okay, product, here I have more product than I have reactant, and that's okay. But I do have some of each present, and they are the same. And they are constant over time. Okay. Now, how is equilibrium different than reaching completion? Because if you think about it, if the reaction is complete and one of the reactants is totally used up, then my product wouldn't be changing over time either. So how can I differentiate between equilibrium and completion? And the AP loves to ask questions about this. So how might this graph look if the reaction went to completion instead of equilibrium? Okay, well, I would start kind of the same, right? I'd still have all reactant to start with, highest amount, and I would still have like no product to start with. But if it went to completion, how much reactant would I have once the reaction is over? I would have essentially no reactant left, right? Or at least not any of one of them I'm limiting. So if I was just looking at the product over time, I want you to see this. If I was looking at the product over time and start at 0 if I don't have any to start with, and then it would level off to some value once equilibrium's reached, it might be difficult to tell, just looking at the product in this case, whether or not equilibrium versus completion has been reached, right? So reactant is going to be very telling in this situation. One or more of the reactants has to be completely used up to get to completion. Okay, and notice how that's different from this previous graph. I have both reactant and product in my container. I need some of each. If I am missing one of my reactants or products, if one of my reactants or products is 0, then I'm not at equilibrium. I need some reactant and some product. And I'm really hammering this in because from a conceptual standpoint, you might see a lot of questions about this. Okay. So here's an example, just quickly. Here's a concentration versus time graph for the same reaction, different concentrations I've started with in different situations. Just take a moment, mark with a vertical dotted line the time at which equilibrium is reached, and then answer this question. Okay, so when equilibrium is reached is when my concentrations are constant. Notice in this situation, I start with all H2I2 to start with, all my reactant and no product. And I can still reach equilibrium because at a certain time, my concentrations are constant. I've not reached completion because I have both reactant and product in my container. Nothing's been completely used up. And you might have yours slightly shifted to the left, slightly shifted to the right. This isn't the best graph of them leveling off at the same time, but we do the best we can here. In this situation here, I start with all HI and no H2I2. So in this case, I actually start with all product in my container and no reactant. But notice I can still reach equilibrium. I've reached a point in time where my concentrations of product and reactant are both constant and not 0. So they have to be constant and not 0. So to answer this question, yes, equilibrium can be reached by starting with product instead of reactant. You can start with all reactant or all product or 50-50 mix or any mix, okay? You can still reach equilibrium. There's no set initial conditions you need to reach equilibrium. So there are no necessary amounts of reactants needed to achieve this state, okay? Also, by the time you reach equilibrium, sometimes you'll have almost equal amounts of product and reactant. Sometimes you'll have mostly product. Sometimes you'll have mostly reactant. There's no set values that make it, this is the way it has to be at equilibrium. We're going to examine different situations where you'll see different things here. And again, you can start with either products or reactants, but a stipulation is you have to have both reactant and product present. So we're going to write this thing called the equilibrium constant. So for any general reaction, okay, here's just a general reaction. There's two reactions going on. There's a rate going forward and the rate going in reverse. And remember from last chapter, if this is, let's say this is an elementary reaction, then my rate going forward would be Kf, right, the rate constant, A to its coefficients, B to its coefficient. We just do the rate, we just do the reactants. And the rate in reverse would be using these as my reactants. So it would be C to the C power, D to the D power. At equilibrium, I know that the rates are equal. So I can set these two things equal to each other, just showing you deriving something. And I can rearrange this to get a ratio of the forward rate constant over the reverse rate constant. And if I do that, I get this expression that looks like this. We are going to call this the equilibrium constant. You might see this represented as just big capital K. You might see it as K with a subscript EQ. You might see it with K with a subscript of C to stand for concentration. There's a couple different ways to write it depending what resource you're using. But it's really simple to write, okay? It's an so first of all, the equilibrium constant for any general reaction, we'll write it right here, okay? Kc equals your products, notice, raised to the power, that is their coefficient, over the reactants, raised to the power, that is their coefficient. And these square brackets indicate concentration in molarity. So basically, this is an expression that we can write. If they ever say write the equilibrium constant expression, this is what you're doing. You put Kc or K or KEQ on the left. Okay, as I said before here, I skipped over it. Okay, you might see KEQ, you might see KC, or you might see K. And you put the products to the power of their coefficients on top, reactants on the bottom to the power of their coefficient. This is on your AP Chem formula sheet. But this is a way of giving us information about, are we going to have more product or more reactant in equilibrium? If you have your equilibrium concentrations, you plug it in and you can get a value for Kc. Now, again, that C stands for concentration. This is in terms of concentrations, okay? Kc, we're going to see, always has the same value at a given temperature, okay? If we go back to how Kc was derived, it was the ratio of the rate constants. So if you change the temperature, you actually are changing the rate constants, so temperature will affect the equilibrium constant. And what you're going to notice is, hey, depending on what the orders are, these concentrations aren't all going to cancel out. So they said, hey, let's not worry about that. Let's just make Kc unitless. No units. So you don't have to worry about plugging in with units for Kc, which, as I know, is a very rare thing to do in AP Chemistry, to not have to worry about units. Okay. And it also does not depend on the reaction mechanism. It's only going to depend on their ending products and starting reactants. So let's just practice actually writing this expression. So here's a reaction. Write the Kc expression, or the equilibrium constant expression. Take a moment and do that. So I should have either just a capital K, or K sub EQ, or Kc, however you want to write it on the left. And I put my product in square brackets, raise it to the power that is the coefficient 2. I put my two reactants, okay, I don't put a plus sign between them, they should be multiplied together. Put them each in square brackets and raise them to the power that is their coefficient. Simple. Okay. Take a moment, try this example, do it out for all three just for practice, and check your work. Okay, so here's the first one. Notice to make sure you keep the subscripts. Okay, here's the second one, products over reactants raised to the power that is the coefficient. And here's the last one, and just notice if there is a charge in there, if there's an ion, just make sure you keep it in the formula. It's part of the formula. Okay, one more example here. Here's actual data from a lab. I'm giving you a reaction, N2O4, and it's turning into two NO2s. So here's my initial concentrations, and then once the reaction reached equilibrium, the equilibrium concentrations were recorded. I want you to take a moment and calculate the equilibrium constant, which we can call Kc, or K, or KEQ, and for each trial, I want you to calculate it and put it in this last column. Now, K is called the equilibrium constant, so make sure you're plugging in equilibrium concentrations, not initial. So if they give you initial, that's cool, but that's not what's going into the equilibrium expression. You have to plug in your equilibrium values. That's why it's called the equilibrium constant expression. So I'm plugging in this case would be NO2 squared over N2O4, and I'm doing that for each trial using the equilibrium data. Okay, so for experiment 1, just showing what I'm doing. Okay, here's my NO2, square that. Here's my N2O4. I don't have to worry about units because K is unitless, and I get 0.211. And if you do that for each trial, okay, here's the data. Now what you're going to notice is what's happening with K. In each trial, I've started with a different initial concentration. So in this first trial, I've started with all reactant. In the second trial, I've started with all product. Okay. In this third trial, I've done a 50-50 mix. And in the fourth trial, I did 75% reactant and 25% product. And in each situation, I was able to reach equilibrium. And without calculating this equilibrium constant, it looks like these values are really different from each other. And notice, depending on what initial amounts I have, I will get different equilibrium concentrations. But once I plug them into the equilibrium constant expression, that's why this is called a constant. Because as long as my temperature is constant, this ratio of NO2 squared over N2O4 is constant, which is pretty cool for this reaction. So things to note, which you'll see. Notice it doesn't matter what initial concentrations you start with. All reactant, all products, or a mix, you can reach equilibrium. Depending on your initial concentrations, your equilibrium concentrations will vary in each trial. But once you plug into the equilibrium constant expression, the ratio will always be the same as long as the temperature is the same. Notice that as well, once we've reached equilibrium, the reactant or product is never zero. I have some reactant present, I have some product present. This is telling me it didn't go to completion, so if these values are constant, I've reached equilibrium. Let's answer this question. If I had gone to completion instead, okay, what would I have expected the N2O4 concentration and the NO2 concentrations to be if trial 1 had gone to completion? Take a moment and answer that question. Okay, so if it had gone to completion, all this reactant, 0.1 molarity, would be used up, right? So if I go to my stoichiometry, okay, N2O4, first of all, would be a 0, right? It'd be completely used up. If I had more than one reactant, at least one of the reactants would be completely used up. And then NO2, if all 0.1 molar were used up, and for every one N2O4 I get 2 NO2s based on the stoichiometry, I would get 0.2 molar NO2 formed. So notice in each of these cases, the NO2 amount is less than this theoretical yield I would get if it went to completion. And notice in all of these cases, the reactant is higher than 0. Okay, so make sure you're able to tell the difference between equilibrium and completion and not just saying the concentration's constant. Because once you get to completion, your product would be constant. You wouldn't be making any more of it. But just knowing and explaining the difference, because I've seen that asked a lot. Okay, so as you can see at equilibrium, the ratio of NO2 squared to N2O4, what's your equilibrium constant, is constant no matter what the initial concentrations are. In other words, the value of K is constant. This ratio will always be the same as long as the temperature is constant. Even if there's a change in concentration or a change in pressure, it's not going to affect the equilibrium constant.